Hello class, this is CSE 5720, section 2, week 3, spring 2025, no, fall 2025. I'm time traveling here. Alright, so, we are currently in week 3, and to make sure that we're on track, I want to make this video describing chapter 7 and our current assignment as well. So, Chapter 7 is all about the ER model, and that is used to... The ER model is a means of identifying entities to represent and relationships between those entities. Once we have an ER diagram, we can transform that into a set of relation schemas and some constraints. So, I'm going to skip over the overview of the design process, but it is a multi-stage process. For example, you gotta figure out what is needed in the enterprise, and once you have that, you gotta apply a data model and turn that into a conceptual schema of the database. There are a few things we want to avoid when it comes to designing a database schema. That is redundancy and incompleteness. So here's a bad example. A university represents its... let's say a university provides a listing of its class sections, but not information about the classes themselves. That means, if we want to display information about a class, we gotta have it offered immediately. So what makes this example bad is, well look, there's some redundant information, see? We are repeating information because we have two separate instances of the same class being taught in different classrooms. Additionally, what if the university wants to offer a brand new class, say, Intro to Microtonal Music Theory, but they don't have anyone to teach it yet, and they haven't found an appropriate building to teach it in yet? Well, they have to put in not applicables, or, as we'll see, null values for those fields. And although it can be done, it's hard to represent the information that we want without having to stick in null values for the parts that aren't applicable. So this is a bad design. A much better way is to split this into classes, course offerings, and sections, instances of classes being taught. Course offerings, those describe what classes are being offered regardless of when it's offered and who's teaching it. If we want information about that, that is more appropriate for sections. So we need two tables for this. One for the classes being offered, and the other one for instances of classes being taught per semester. Because sometimes classes are taught in specific semesters. Let's say Intro to Microtonal Music Theory is only offered in the fall, but not in the spring. So, we want to represent that information in a table of class sections. If you want to represent Intro to Microtonal Music Theory on its own, that is more appropriate for classes, class offerings, courses. So the ER model, the entity relationship model, was developed to facilitate database design by allowing specification of an enterprise schema that represents the overall logical structure of the database. It's a way of visually representing entities, relationships, and their attributes. So an entity is a real-world thing or object that is distinguishable from other things or objects. For example, a train is a thing, and so is, although this would be a fictional example, a Pokemon. So trains are things, Pokemons are things, your phone is a thing, and they're all distinct from one another. They also have their own attributes associated with them. So entities can be concrete things like trains, or abstract fictional things like, as I said, Pokemon. I guess a physical Pokemon could be a thing if you count them as plushies. But they can also include abstract things like class offerings or a flight reservation. And for each entity, every entity has a set of properties, and some of them may uniquely identify an entity. An entity set is a collection of entities that share the same properties. So we can have multiple trains, but they have all the same attributes between one another. Say, speed, capacity, manufacturer. How about for our university example, all the instructors of a university form an entity set of instructors. They have all the same attributes. The same is true for the students of our university. They also have their own attributes as well. Entity sets don't need to be disjoint. We can generalize the notion of student and instructor by having an entity set of person, and then they can fall under either one of these two categories of instructor or student, or they could fall under both. A student could also be an instructor. Let's skip that for a little bit. An entity is represented by a set of attributes. So every entity, as I said, has a set of attributes. A train has a top speed. A train also has a capacity. A Pokemon has several attributes to it. Pokemon type, or maybe two types. Health points, attack, defense, special attack, and so on. There's also nature. Yeah, Pokemon have attributes of their own that are all distinct from a train. And they're all distinct from a phone. So a student has an ID, a major, a name. A student may also have more than one major, and a student also has a total number of credits. An instructor has an ID, a name, a department, or more than one department, and a salary. These aren't the only attributes we might find in a university enterprise, but this is just enough for us to get started. Each entity has a value for its attributes. So a train could have a maximum speed of 80 miles an hour and have a maximum capacity of like 500 passengers. A student could have a particular ID of 65535 and 121 credits. A real-life university typically has dozens of entity sets, but let's just focus on the ones for instructor and student. We can form relationships between any two entity sets if they interact with one another in any way. For example, we can form relationships between instructor and student if instructors are advisors to students. If we have multiple instances of the same relationship, we call that a relationship set. We're not talking about individual interactions between a particular student and a particular instructor. We are talking about the same kind of interaction in general between instructors and students. We say that student and instructor participate in the relationship set of advisor. A relationship instance, if we want to talk about a specific advising relationship between instructor and student, we call that a relationship instance. Say, Katz and Shankar. Katz is advising Shankar. Shankar is being advised by Katz. The entities in a relationship perform some function, and we call that a role. Most of the time, usually, we don't need to specify roles. They are usually implicit, and they don't need to be specified. But sometimes there are cases where we need to specify relationship. Yeah, there are cases where you have to specify the roles in a relationship, such as with the recursive relationship set, such as course prerequisites. So, say this class here, CS401, requires 3 different prereqs: CS301, 202, and Math 101. We can represent prerequisites as ordered pairs, C1, C2, where class C1 requires class C2. So we can say class CS401 requires class CS202. But it also requires Math 101 and 301. We also need to represent those, but we represent them using different ordered pairs. So CS401, comma, Math 101, and then CS401, comma, CS301. Here's what it looks like if we were to organize it by the same way as we did with our student and instructor relationship sets. You can also have attributes as part of a relationship set. For example, these dates represent when an instructor became an advisor to a particular student. And we ought to be able to identify individual relationships without having to use those descriptive attributes. What I'm talking about is the notion of a primary key. So, a primary key is a set of attributes that we can use to uniquely identify different entities within the same entity set. In the case of instructor and student, well, that's easy. It's the student ID, or in the case of instructor, instructor ID. Either way, we have IDs for both entities. We typically use some combination of instructor and student ID to uniquely identify every relationship in our relationship set. Why wouldn't we want to use the date as part of, or as our sole attribute for the primary key? Because it's possible that an instructor may become an advisor to two different students on the same day. So date is disqualified from being a primary key. We'll talk more about primary keys for relationship sets in a little bit, but notice that we have two participating entity sets for our advisor relationship set. But interestingly, we only have one participating entity set for our prereq relationship set. Let's focus on the one for advisor, the one where we have instructors and students participating in the advisor relationship set. We call that a binary relationship set. Sometimes you might have relationship sets with more than two participating entity sets. They're generally called non-binary relationship sets. We can also refer to them by the degree. That is the number of participating entity sets. So binary is 2, ternary is 3, and so on. So here is an example of a ternary relationship where we have instructors being project guides for students working on a project. And that's something that a binary relationship might not be able to capture on its own. For each attribute, there's also a set of permitted values. If you think about a phone number, for example, the domain of phone numbers is basically the list of all 10-digit numbers ranging from starting at all zeros and ending at all nines. So somewhere in that list is your phone number and my phone number. I think I just accidentally doxed everyone. But on the other hand, good luck finding our phone numbers in there. So that is a domain for an attribute. It's the set of all possible values for that attribute. Here's a few other examples. A university course must take place in the fall, winter, spring, or summer. So that set of 4 seasons, we can call that the domain for the attribute semester. Formally, an attribute of an entity set is a function that maps from the entity set into a domain. We can also express, since an entity set may contain several attributes, we can describe an entity as a set of attribute and data value pairs. So for example, ID 76776, name Crick, department name Biology, and salary 72,000. That describes a particular individual who works at the biology department. An attribute in the ER model can be characterized by one of a few types, and some of these types are not mutually exclusive, by the way. For example, we can have simple attributes whose attributes cannot be subdivided into smaller parts. We can also have composite attributes whose attributes consist of subparts that we call component attributes. We can also have single value attributes where an attribute for a specific entity has exactly one value. Sometimes an attribute for an entity can have more than one value. Pokemon types. Pokemon have one type, but they can also have two types. And then there are some games where they introduce a third type. Well, not official games, I'm talking like fan-made games where they add a third type somehow. So we have simple attributes, composite attributes, multi-valued attributes, single-valued attributes, and the last type is a derived attribute, where the value of an attribute is derived from the values of other attributes. So here are a few examples. An ID, we cannot divide an ID into smaller parts. An address can be divided into smaller parts. A student or instructor can only have one value for an ID, that is a single value attribute. So a simple attribute can also be a single value attribute. But a simple attribute could also be a multi-valued attribute, like a phone number. An instructor could have more than one phone number. An address is a composite attribute, but it could also be a single value attribute. Or rather, its components could be all single value attributes. The point is, we need to have one value for the address, even though the address is split into multiple parts, like street, city, state, zip code. And then the street itself is further subdivided into house number and street name, and if applicable, apartment number. What about a derived value? Well, you might have some values for an attribute that are not stored, but rather calculated on the fly using a getter function. For example, the number of students assigned to an instructor, we can figure that out just by counting up all the students. So here are those composite and component attributes. Name and address are composite attributes because they're made up of different component attributes. Finally, an attribute can take on the value of null if it represents not applicable, or it represents a value that is missing, or a value that is not known. Null, representing not applicable. For example, an instructor lives at a house, so apartment number does not apply. A student does not have a middle name, so middle initial does not apply. So that is not applicable. How about a missing value? Let's say an instructor works at a university, but in the database, their name is null. That indicates that their name is missing. It exists, but it's not yet known in the database. So that is value missing. How about value not known? Say that same instructor has a phone number of null. That indicates that we either the instructor doesn't have a phone number, we say that's not known, or it's not known to the database, so we call it missing. But we don't know whether it's not known or missing. Since every instructor has a name, we expect null values for an instructor name to mean this instructor has a name, but it's not in the database. What if their name literally is null? The string null. Well, I hope your database has a means of differentiating null the value and null the string, because to enter that into a database can and has caused problems. You can watch this video in your own time, but the point is, don't choose null as a license plate. Let's talk about constraints. So, an ER schema may also define certain constraints that a database must adhere to. Here we're talking about mapping cardinalities and participation constraints. So a mapping cardinality This is going to be more familiar if you have taken a course that touches on set theory. So for example, let's consider how instructors are advisors to students. The simplest example is one-to-one. One instructor advises one student. That's a simple example. But typically in a university, there are going to be way more students than there are instructors. Therefore, by the pigeonhole principle, we need a one-to-many mapping between instructors and students. Therefore, one instructor may be advising multiple students. We can also have a many-to-one mapping. A student may have more than one advisor, such as, say, joint advising between multiple instructors, or advising between instructors from multiple departments, such as if they're dual majoring. However, in a typical university, it's going to be way more complex than that, so it's likely going to be a many-to-many mapping cardinality. That is, instructors are advisors to more than one student, and students may have more than one advisor. You notice how there are a few unpaired entities in our sets? Well, that's because the exact definition for these mapping cardinalities state that an entity in one set is associated with 0 or more entities in the other set. In the case of this, where B is supposed to be students, that means a student has yet to be assigned an advisor. In the case of this, where A is instructors, that means an instructor might not be tenured enough to become an advisor for a student. In other words, in our university enterprise, we want every student to have an advisor, but not all instructors are needed to be advisors. As I said, in our university example, we want every student to have an advisor. If we can pull that off, we call that total participation. Every student entity participates in the relationship set of advisor. So every student should have an advisor. We call that total participation. But not every instructor is needed to participate. We call that partial participation. We say that the participation of the student entity set is total if every student participates in the relationship. We also say that the participation of the instructor entity set is partial if not every instructor is participating. So we talked about two different entity sets, instructor and student. How do we refer to or distinguish between individual instructors and students? Typically, we just go by their name. There's several pitfalls behind that, such as, hey, what if two people have the same name? Or a special case where someone goes by a last name, which is someone else's first name. That's why we use different attributes to distinguish between different people. If that attribute is some sort of ID and everyone has a unique ID, boom, you have a primary key already. The point is, we need a key, and every entity must have a unique key. Or rather, I should say, every entity in an entity set must have unique values for that key, such that no two entities have the same exact values for every attribute. We talked about this in Chapter 2, and my apologies, I never made a video for Chapter 2. I might have to make that sometime if I can. But basically, in Chapter 2, we talked about the notion of superkeys, candidate keys, and primary keys. So we can use a primary key to uniquely identify entities, but we can use it to uniquely identify relationships. Basically, in a relationship set, if you have primary keys for the two participating entity sets, the primary key for the relationship set is going to be some combination of the two entity sets' primary keys. However, there are several options for this, depending on the mapping cardinality. So, before I get to that, notice that the wording in the slide is super key. And that's because when you are creating a key for an entity set, you might have some combination of attributes, but there might be a few attributes that are unnecessary. We call that a super key, but eventually we're going to whittle it down to candidate keys. And once we whittle down all the possible candidate keys and remove any unnecessary attributes, once we whittle it down, we find a primary key that we can use to identify every entity in an entity set, but also every entity in a relationship set. So, we can call this a super key, but we can also call it a primary key we can also call this a primary key under a specific condition, and I'll get to that in a little bit. Basically, depending on the mapping cardinality, you might need to use both IDs, or you can use one ID. And I'm talking about the student and instructor IDs here. Can we add the date? Yes, we can, but this makes it a super key. That means there's going to be some attributes that are needed to uniquely identify every possible relationship in our set. It means there are going to be some attributes that aren't needed, and in this case, the date is not needed, so we can just take that out. So, if we want primary keys, here are the options. If you have a many-to-many mapping, you need both primary keys from both sets. I'm going to use the example of students and instructors. So, if A is instructors and B is students, in a many-to-many mapping, we need both IDs. If it's a one-to-one mapping, we can use either ID. If we have a many-to-one mapping, we use the instructor ID. And if we have a one-to-many mapping, we use the student ID. We can use both IDs, but that isn't what's known as a minimal super key. Adding additional information might not add anything new. If anything, adding extra information just adds redundancy that we would like to eliminate. Alright. Hopefully I did a good job at explaining what that is. But let's talk about removing redundant attributes. When we start designing a database using the ER model, we usually start by identifying the entity sets to be included. Once we identify those entity sets, we must also decide on which attributes to include for each entity type. Once we identify all those attributes, we can start to form relationship between the various entities, and it's here that we might find redundant attributes. Let's say at this stage we have the entity sets instructor and department, and we have the following attributes. For instructor, that is ID, name, department name, and salary. And the ID is the primary key. For department, those attributes are department name, building, and budget. And the primary key is department name. At this stage, we can start forming a relationship set between instructors and departments. So let's look at those two entity sets closely. Primary key attributes are underlined. Since we're forming a relationship set between instructor and department, check this out. We have department name as a primary key attribute for department, but it's also showing up here as an instructor attribute. Under the rules of making an ER diagram, turns out this department name attribute under instructor is redundant, so you can just cross it out. Now, this might feel a little bit unintuitive, and that is because in other chapters, we are going to see department name as an attribute for instructor. Why are we eliminating it now? Why now? What? Why? Why? Well, that is because we want to represent the pairing between instructor and department as a relationship. So to do that properly, we need to remove department name as an attribute from instructor. This also makes it so that this also eliminates the premature assumption that an instructor can only be associated with one department, because an instructor may be associated with more than one department. As we'll see later on, if an instructor is associated with more than one department, we can just represent that as an additional table in our database. And we can argue the same thing for students. A student may be associated with more than one department, particularly if they're dual majoring. So we don't need to include the department name attribute for student. Cross it out. Here's another example of a relationship set relating sections and time slot. So section has all these attributes: course ID, section ID, year, and semester. Those are 4 different attributes that form the primary key for section. And then time slot attribute, we have time slot ID, day, start time, and end time. Because time slot ID is already a primary key attribute for time slot, when we form a relationship set between section and time slot, we can find time slot here, we can cross that out. Same is true for classroom attributes. Building and room number form a primary key for that. So if we form a relationship set between section and classroom, we can just cross out building and room number. So these aren't the only entity sets in our university, nor are these the only relationship sets. This is just a sample of all of the needed entity and relationship sets for our university. But if you pair entities according to these relationship set, you should find no redundant attributes. No redundant attributes? How come student and instructor have their own IDs? Well, that's because they're their own IDs. To make it more clear, we could rename student ID into SID and instructor ID into IID. But the point is, these are 2 different IDs. They go by the same name, but they belong to different entities. Again, these aren't the only entities or relationship sets in our database. Page 274 describes even more. But once we have all this information, we can start to make an ER diagram. Let's start with student, instructor, and advisor. So now we have an ER diagram for instructor and student participating in the relationship of advisor. Divided rectangles represent entity sets. The upper rectangle contains the entity name. The lower rectangle contains the attributes. Primary key attributes are underlined. Diamonds represent relationship sets. The name of the relationship goes inside the diamond. Lines link entity sets and relationship sets. So here is our ER diagram for instructors and students. If we include the date attribute as part of our advisor relationship set, we have to connect it with a dashed line. Date also goes in an undivided rectangle. That is for attributes for a relationship set. And again, dashed lines link relationship attributes to relationship sets. By default, an undirected line, that is an ordinary line, no arrowheads attached, by default, that represents a many-to-many mapping. If we add arrowheads, the relationship's mapping cardinality changes. So if we have arrowheads on both the instructor and student, that becomes a 1-to-1 mapping cardinality. If we have an arrowhead on just the instructor, that's a one-to-many mapping. Although it's not shown here, if we just have an arrowhead on student and no arrowhead on instructor, that is a many-to-one mapping. We can be more clear, or we can impose limits by adding labels to our lines. So 0 dot dot star and 1 dot dot star. So these represent limits on how many instructors can participate in a particular relationship, advisor relationship, and how many students can participate in an advisor relationship. So on the instructor side is 0 dot dot star. That means an instructor can advise 0 or more students. The star indicates no upper limit. So this says 0 or more. And on the student side, this means exactly 1. This is just a different way of representing a one-to-one mapping, but you might look at this and think to yourself, the 0 dot dot star applies to instructor and 1 dot dot star applies to student. So this is supposed to be a one-to-many mapping, but again, it's easy to misread this and think it's a many-to-one. So you see the 0 dot dot star, think it's applying to instructor, but no, it's actually applying to student. So think about it this way. It's a bit of a circuitous loop, and I want you to pay attention to the animation here, but an instructor is an advisor to 0 or more students. And a student is advised by exactly 1 instructor. Hey wait, what if... We already talked about how this could be a many-to-many. This could be many-to-many. And you're right. If you want to represent this as a many-to-many, we can replace the label here with 1 dot dot star, meaning a student can have more than 1 instructor for an advisor, but they need to have at least 1. So these labels, these cardinality limits, make our mapping more specific. Complex attributes. So when we list the attributes for an entity set, if any of them are composite, we list the components indented. As mentioned before, primary key attributes are underlined. Name and address are composite attributes, and their components are listed indented. If we have a multi-value attribute, we enclose it in curly brackets. If we have a derived attribute, we put parentheses after the attribute. Sometimes we need to make it clear what roles a entity has in a relationship set. So, course, there's only one participating entity set for the prereq relationship set, but we need to make it clear which one is the course ID and we need to make it clear which one is the course and which one is the prereq. So we have two connecting lines from course to prereq, where one is the course ID and the other is for the prereq ID. So one course is the prerequisite, the other one is the one that requires the prerequisite. Finally, we have ER diagrams for ternary relationships and above. Non-binary relationship sets can be represented as they normally would, but if we add cardinality, mapping cardinality to that, it becomes a little bit tricky. If we add one arrow to a non-binary relationship set, this represents a many-to-one mapping, and it means one project can be guided by at most one instructor. Things get confusing when we add a second arrow. So, if we have this non-binary relationship set and we add an arrow to instructor, that means a project can be guided by at most one instructor. If we add a second arrow, turns out there's some ambiguity over as to what this means. Meaning number one, a student can be associated with only one combination of instructor and project. Meaning number two, a specific project can only be associated with one specific advisor, and vice versa. It gets more complicated when you have hierarchies for a non-binary relationship set. So, in this 5-array relationship set, where we have arrows on entity sets A3, A4, and A5, meaning number one, a particular combination of entities from A1 and A2 can only be associated with at most one combination of entities from A3 to A5, meaning number two. For entity sets A3 to A5, one entity set from one set can only be associated with one combination of entities from the other sets. So, A3 can only be associated with a particular with only one combination of entities from A4 and A5. Same is true for A4. It can only be associated with one combination of entities from between A3 and A5. Same is true for A5. An entity from A5 can only be associated with one combination of entities from in A3 and A4. Are you lost on this? If so, don't worry about it, because the textbook imposes a rule, and that is only one arrow allowed in a non-binary relationship set. So, when it comes to us drawing non-binary relationship sets, we're only allowed to draw one arrow. The last thing I'm going to talk about before I switch to the next set of slides is weak entity sets. So a weak entity set is an entity that cannot be identified by its attributes alone. So its primary key attributes. It requires a foreign key in addition to its attributes to form a primary key. So let's look at the example of, let's say we have a course on 3D modeling. It has these attributes for forming its primary key, which means we have a corresponding 3D modeling course with the course ID as our primary key. What happens if we form a course section relationship set between these two? Well, we find out that we have course ID in both, but they're both primary key attributes, so we can't eliminate either one. What we could eliminate is the relationship altogether. But we want to represent this course section thing as a relationship, not have it be implied through attributes. So an alternative is to eliminate the course ID as an attribute for section. But now we have a problem. This is not enough information to tell that this is section 1 for Intro to 3D Modeling, because we can have a section 1 for Intro to Microtonal Music Theory, and because we've eliminated the course ID for both entities here, we can't tell them apart. For us to tell apart these two different entities, we need extra information in the form of the course ID from their corresponding courses. This makes section a weak entity set, and this also makes course an owner entity set or identifying entity set, because course contains extra information that we need to tell apart different sections. The relationship formed this way is called an identifying relationship, and the weak entity set of section is said to be existent dependent on course, and course is said to own the weak entity set section. As I said, the primary key for a weak entity set, that is not enough information to tell apart different entities within the same set. So we can't tell whether this is Intro to Microtonal Music Theory or Intro to 3D Modeling. It's only when we add the primary key attributes from course that we can tell them apart. So we can't call this a primary key anymore. We call it a partial key or discriminator. So yeah, once we add the primary key attributes of course, are we able to identify or distinguish between different sections. And we represent a weak entity set using additional symbols in our ER diagram. So a double diamond represents a relationship set. It represents a relationship with a weak entity set. Double lines connect to a weak entity set. They also represent total participation. And discriminator attributes are underlined with dashes. Due to how all section entities depend on some course entity, this is necessarily a one-to-many mapping. One course can have many sections, but every section, the existence of all these sections depend on some course. So this is total participation, hence this double line connecting section to the diamond. Oh, double diamond. Here are a few other things about weak entity sets. A weak entity set can participate in other relationships, even one where it's the identifying set of another weak entity set. And a weak entity set can have more than one identifying entity set. Its primary key consists of the union of the discriminator and the primary keys of the owner entity sets. So this entity set yellow has a primary key that is its discriminator, and the primary keys of green and red. So to distinguish a weak entity set from our other entity set type, we call the other ones strong entity sets. So what makes a weak entity set weak is it doesn't have enough attributes such that it can stand on its own. Its existence depends on something else. If that is the case, we have a weak entity set. But if we have the case where both entities can stand on their own, they can exist without each other, those are strong entity sets. Does the existence of a bus depend on its driver? And does the existence of a driver depend on the bus? If the answer is no, then bus and driver are strong entity sets. If the existence of an account doesn't depend on the bill, but bill depends on the account, then we have bill as a weak entity set, an account, because the existence of a bill depends on an account, that forms a identifying relationship set between bill and account, where account is a strong entity set and bill is the weak entity set. Here's the final ER diagram for all our entities and relationship sets in our university. So this is section 7.5. In section 7.6, we're going to turn this into a database schema. But first, let's talk about your homework. I'm actually going to demo part of your homework and see how we can turn our description into an ER diagram. So let me just switch over to the homework. So you are allowed to use software to help draw your ER diagrams. What I'm going to do is I'm actually going to, this is just a sprite thing I was working on earlier. What I'm just going to do is draw the diagrams in here. So I'm just going to use paint.net for that. So let's do this. We have the following entities with the following attributes, and we have the following relationships here. Let's do 2 of these entities and 1 of these relationship sets. Let's do customer and car. So let's do customer first. That's a little bit easier. So I'm just gonna do that. That's not how it works. So we have our, let's call this customer. And the customer has several attributes. One is name and policy number. And policy number is a primary key attribute, therefore we underline it. Okay, so now we have our entity for customer here. Let's do car next. So car has make, model, year, and vehicle identification number. Let's draw a brand new rectangle for that. I might have to make it a little bit wider here. Let's do that. Let me just draw a brand new rectangle. Let's call it car. So we have make, model, year, and VIN number. Okay, this raises a natural question. What's the primary key? Well, a vehicle identification number actually contains all the information needed to identify the car's make, model, and year. But depending on how easily that can be parsed, we might want to make that a separate attribute. So depending on how you make your database, we could make model, year the primary key, or since every VIN should be unique, we can make that the primary key. So you have several options for the car. I'm just showing you one of several options, depending on how you want to go about representing this in a database. So now we have customer and car. Nice. Alright, the next step is let's form a relationship set between customer and car. So for that, I need to draw a diamond. So let's call this relationship drives. So a customer drives a car. There's another option for the name, and that is car is driven by a customer. So we could call this drives, or we can also call it is driven by. Either one will work because roles are implicit. So we can connect these two entity sets with lines to our relationship set. So customer drives a car, or alternatively, a car is driven by a customer. How many cars does a customer have? Well, a customer drives one or more cars. So you can just write that down here as one dot dot start. And a car can be driven by, it's a little bit complicated because a policy could cover a customer and more than one people who is in association with the customer. But that means we need to have some other, it means we might need to add a bit more information here. But let's just say that in this toy example here, a car can only be driven by one customer. So if we impose that limit, we have 1 dot dot 1. Again, this is just one of many ways to go about this. And in fact, I actually give you the option to add additional entities, attributes, and relationships to this entity set. So we can make this more complex and add that. Actually, no. Let's leave it like this for now. If we want to represent other people who could drive the car, who are associated with the customer, we would need to find some way to do that. In this simple example of a customer has one or more cars, it's possible that we could just have an extra attribute here of other drivers. They are associated with the customer somehow, and they can also drive a car. But does this make this one dot dot star? Well, it's only one customer, so maybe you should just leave that as one dot dot one. So what this represents is a customer or someone associated with the customer can drive the cars that are insured under the customer's name. So no car swapping. Is this all making sense? Well, with this simple example here, hopefully I've given you enough to at least start on drawing the diagrams for our enterprise here. So we can be as complex or as simple as we want, and I've given you that freedom to do exactly that. So if we accept the stipulations that a customer can have one or more vehicles and a car can be driven by exactly one customer, then we have completed our ER diagram for customer and car. One customer drives one or more vehicles. One car is driven by exactly one customer, or can be driven by other drivers in association with the customer. Let's try to represent other drivers. Well, I did my best, and this might not be the best way to represent it because it suggests that a car can be simultaneously driven by the customer and other drivers in association with the customer. So I did my best to try to represent it, but this might not be the best representation of trying to represent other drivers who are covered by the same policy. Yeah, this exposes the nature of drawing an ER diagram, and that is there might be more than one solution to the same problem. It's just a matter of finding the best solution that you can find. So, as I said, this might not work. Or maybe you can make it work. My point is, whatever additional information you wish to add to your ER diagram, you might struggle to find a perfect solution for it, because, again, there might not be a perfect solution. So it might mean that something like this might be more suitable for representing a customer drives a car relationship. So a car can only be driven by one customer, and a customer can drive one or more cars. Yeah, this might also be an easier way to represent the same thing without having to add on other drivers as part of a without having to add other drivers as part of a identifying relationship set. So there you go. Here is one of many possible ways that we can represent one customer driving a car with possibly other drivers in association with that customer. Okay, so that is one relationship set and two participating entity sets for question 1. Maybe we could also add accident. So let's just do that for completeness. So accident information could be represented in a rectangle here. So let's just draw that. Let's just add that. So if a car gets involved in an accident, we want location, date, and cars involved. So actually, a location and date might be not be enough, because if two cars get into the same accident, do we log that as one accident or two accidents? Also, what if two accidents happen at the same time, but they're unrelated cars? So let's add an extra attribute here. Accident ID. Let's use that as our primary key. Oh, by the way, do you want to represent location as an address or a latitude and longitude, or both? I'm not going to show it here because I have to rewrite all the text, but that depends on whether you want to use address, latitude, or longitude, or both. It makes sense if you want to use an address because an accident could take place literally in someone's front yard. Then we can just flag the address. But what if an accident occurs in the middle of nowhere and all we have to go by is the latitude and longitude? Depending on what information we have, we could use either one or both. So for completeness, we might want location to be a composite attribute that contains an address, which is itself a composite attribute, and latitude and longitude. So again, that's just one of several ways we want to represent our enterprise. So let's go ahead and add our accident information. And a car can be involved in an accident. So let's call this involved in. How many cars can be involved in an accident? Well, the answer is one or more. It could also be 0 or more if it turns out the case was fraud. Or it turns out the case was a test case. So we want this accident report to be one to many cars. So I'm going to represent that by drawing an arrowhead on accident, and we can have 0 or more cars involved in our accident. Can you have a car accident with only one car? Yes, you can. In that case, you probably just crashed your car into a ditch or something. Can you have an accident with more than one car? That might be what we think of when we think of car accident. 2 cars crashing into one another, with varying degrees of damage and bodily harm. So we want exactly one accident report, and we want to have... There's no upper limit to how many cars can be involved in an accident, as gruesome as that may sound. But we allow for the possibility of 0 cars in an accident if it turns out the case was fraud. But maybe we don't want fraud, or maybe we want that as a special test case. So if that's the case, you want 1 car minimum in a car accident. So that's how we can represent car accidents, cars involved in a car accident. There we go. Alright, so that is for problem 1. You want to try an example in problem 2? Of course you do. Let's try it. Okay, so that is its own thing. Let's try now making an ER diagram for player and team. And let's do the relationship set of which players play in which team. So let's do player first. That's the wrong shape. I want a rectangle. So let's do this real quick. So we have a player name, player ID, position, and jersey number. Name, player ID, position, and jersey number. So which is our primary key? Well, if we assume that every player has an ID and we expect it to, player ID is our primary key. Let's do team. So the attributes for that are team name, team ID, and city. So let's add that. team ID, city, team name. And if each team has a unique ID, we can use that as our primary key. There we go. Now let's represent our player playing in a team. So let's just add a diamond here. Let's call that plays in. So a player plays in a team. Okay, we're almost there. How many players can play in a team? Well, there's no upper limit to that, but what's the lower limit? Can a team exist with no players? Do you have a team? Can you have a team with 0 players in it? Well, let's just say for the sake of database handling, let's say we can have a team with as little as 0 players. Hold on. Actually, that was the wrong side. So, a player can... So let's start on the player side first. Can a player play in more than one team? For the purpose of this discussion, let's say no. So a player plays in... Can a player play in 0 teams? If a player is retired but is somehow associated with the sports thing anyway, let's just say a player could just be retired or removed due to controversy. So let's just say a player plays in 0 or more teams. Actually, no. A player plays in 0 or 1 teams. Because a player can only play in 1 team at a time. And then, a team is composed of 0 or more players. Because if the team is empty, we need still some way of representing the whole team. So let's just put down 0 ... star. There we go. Here is our player-team relationship. A player plays in a team. A team is composed of 0 or more players. A player can only ever play in 1 team at a time. So that is our information for player and team. You want to try a match? Of course you do. Let's add that in, just real quick. So match has several more attributes. So match ID, opponent team. I'm just drawing this off screen right now. So So we might need to refine this setup a little bit more, but let's just say a match ID, every match has a unique ID. How many teams do we need to play? How many teams can match up against one another? Well, before we answer that, let's add this diamond here. And add the lines necessary to connect it together. Here we go. So a team Okay, so now I'm hitting a problem here where I have player plays in a team, but a team plays in a match. So let's say, let's call it goes up against in a match. So there's several ways you could go about naming these relationships as well. But how many teams can face off Actually, face-off is a better name. So how many teams can face off against one another? And how many teams can be in a matchup? Well, a match should involve two teams, if you think about it. Because typically it's one team versus another team. So we have to say 2 dot dot 2. So a match is where we have a face-off between exactly two teams. And a team can play in a face-off in 1, 0 or more matches. Because if this is a newly formed team, they might not have any matches yet. So let's just do 0 dot dot star. There we go. So feel free to refine this however you want. But it's also possible that this might not be complete, because we would need 2 team entities. We might need to do something like this, where one we have main team and opponent team. And if we have an opponent team here, that is the team ID over here, we might not need this attribute in match at all. So we have a match ID, but we have a main team and an opponent team. But if we identify like this, then yeah, there's several ways we could go about answering this question here. And I'm just giving you one of several possible examples. It's one of possible ways to answer it. So we might need to identify in a face-off which roles are which. So really this is a unary relationship where 2 teams match face off against one another. If we are able to identify which role is which, then we have to say, okay, so a main team can face off in exactly 1 match. I guess we need to put 0 dot dot star here and here. Again, this might not be the right answer, but we're doing our best to represent. Yeah, there's more than one way to answer this, by the way. So this is just one of, yeah. And because we have an opponent team and a main team, and we have their IDs and all, we don't need to add a opponent team attribute here anymore. Oh, but I do want to rename this one to home team. So there we go. Home team and opponent team. Actually, that might not be the best one either, because they could be away also. Okay. Did my best to try to represent players, teams, and matches. There might be more information that we want to include, and I've added for you coach and stadium. You might want to add that information in as well. A coach coaches a team, or they could coach more than one team. A team plays in a stadium. Or rather, a match is played in a stadium. So we can add that extra information here as well. So really I've given you the whole answer for problem number 2 if we don't include any of the optional things here. Coach, stadium, and these relationships here. Okay, so now that we have an ER diagram, how do you go about turning them into relationship schemas? How do you turn them into a schema that we can then use in our database? That's what we're going to talk about next here. So once we have our ER diagram, we can turn it into a schema. Let's begin with a few simple examples. So we have department, instructor, and student. Let's start with student. So these are strong entity sets with simple attributes. All we gotta do is list them out. We have the name of our entity set followed by our attributes enclosed in parentheses, like we're trying to declare a class. So this is for a student, and my camera is obscuring the student. But we do this for strong entity sets with simple attributes. So student, and in parentheses, ID, underlined, name, total credits. The same is true for instructor and department. So department name is underlined, billing, budget, instructor, ID underlined, name, and salary. If we have a complex attribute, we don't need to list every attribute. We only need to list the component attributes. So we don't need to include the name, we only include the attributes that make it up. We don't need to include address, we only need to include the attributes that make it up. But since street is also a composite attribute, we don't include street, we only include the attributes that make it up. So here's the schema for that. ID, first name, middle name, last name. It says middle name, but it says the middle initial here. Oops. Street number, street name, apartment number, city, state, zip code, and date of birth. So some of the names might not be lining up. Is that errata or what? We don't include derived attributes because that can be handled by a function that is supported by a different data model. And we don't include multi-valued attributes because that requires a lookup table. So if we have a multi-valued attribute, we need an extra table whose primary keys are the ID of instructor and the phone number, which is also part of the primary key. So an instructor can have one or more phone numbers. So as I said, this is literally just a lookup table of phone numbers. In general, if an entity has a multi-valued attribute, we add an additional relation for that attribute. The relation's primary key is the union of that entity's primary key and the multi-valued attribute. So instructor can have one or more phone numbers. We add a relation for instructor phone number where the primary key is the instructor ID and the phone number. There's a special case for if we have a entity set with only one primary key attribute and only one multi-value attribute. So let's look at time slot. Normally, this requires adding an additional relation schema where time slot info, so day start time and end time, that is a multi-value attribute for time slot. So we add another table, let's call it time slot info, where we have these attributes as part of our primary key, but we also add time slot ID as part of our primary key. But wait, this relation now has all the same attributes as time slot, so why don't we just use that as the schema for time slot, so we don't need to add an extra table. Here's how we do weak entity sets. So now we have course and section, which as we've seen are weak. No, course is a strong entity set, section is a weak entity set. Course is the identifying entity set for section. Since identifying section requires the primary key of course, the relation schema requires that plus the discriminator attributes. So we write section as course ID, section ID, semester, and year. Formally, the primary key of a weak entity set is the union of the identifying entity set's primary key and the weak entity set's discriminator. So all the attributes that are underlined, regardless of it's solid underline or dashed underline, they are the primary key for section here. The attributes of a relationship set consist of the union of the following sets of attributes. So now we're talking about making schemas for our relationship sets. So all of these slides were how to make schemas for entity sets, including entity sets with composite attributes, entity sets with derived attributes, entity sets with multi-valued attributes, and weak entity sets. So now we are making a schema for a binary relationship set. So what are the attributes for this? Well, it's going to be the primary keys of the participating entity sets plus whatever descriptive attributes there are. So we have instructor and student participating in the advisor relationship. The schema for advisor is going to be the ID of instructor and student. It could be both, or it could be one of them. We'll talk about that in a little bit, but it's the same rules that we discussed earlier. And then we have the date. So if we assume a many-to-many mapping between students and instructors, and we also include the date attribute, then the relationship set advisor is represented by this schema. We need to rename the IDs because they're both called ID, and we need to tell them apart. So instructor ID and student ID. We also have the date. That is not a primary key attribute, but we include it anyway, but not underline it because we need to add the date. And remember, there are different options for the primary key depending on the mapping cardinality. So if it's many-to-many, we need both IDs. If it's one-to-one, turns out there are two options for this. If it's many-to-one, we only need the instructor ID, but if it's one-to-many, we only need the student ID. To simplify the rules, the primary key of the entity set on the many side of a relationship set serves as the primary key for the entire relationship set. There are only two special cases for this. If both sides are arrows, either primary key will work. If neither sides are arrows, you need both primary keys. How about a non-binary relationship set? Well, let's assume that project also has its own project ID of its own. So a lot of the same rules apply for a non-binary relationship set. So if we have a non-binary relationship set here, where we have instructor, project, and student, we can create a schema for project guide whose primary key is all three primary keys of instructor, project, and student. We formally say that this is the union of the three participating entity sets' primary keys. So we have an instructor ID, a student ID, and a project ID. If we add an arrow like this, then the primary key is the union of the participating entity set's primary keys, except for the one on the arrow side. And this is the only case that we consider because we impose a limit of only one arrow maximum for a non-binary relationship set. Here's one thing that we didn't really talk about, and that is foreign keys. Because this schema, and I guess by extension, this schema, project guide is a schema that references the schemas of instructor, project, and student. So there is necessarily a foreign key constraint. In other words, we can only add an entry to project guide if the relevant instructor, student, and project exist. That's what it means to have a foreign key constraint. We can only add something to a database if what we're referencing exists. It might be a little bit simpler to illustrate with a binary relationship set. So let's say we form our schema for advisor with attributes instructor ID, student ID, and date. We can only add a entry to advisor if the instructor and student exists. This is what it means to have a foreign key constraint. We can only add an entry into advisor if the instructor and student exists. So for events, here is our entire ER diagram. And this is all the schemas for all of our relationship sets. Foreign key constraints aren't shown here, but in general, wherever we have a relationship set schema, the entity sets being referenced, those are your foreign key constraints. So advisor has foreign key constraints since it's referencing student and instructor. Prereq also has a foreign key constraint because it's referencing course IDs. Teaches also has foreign key constraints because it's referencing a class section and an instructor. We can't add a teaching assignment unless the relevant instructor and section exist. So, we're done. No, we're not. It turns out there are a few things we can eliminate still. So we can make the schemas for all of our entity sets, but when it comes to making the schemas for our relationship sets, there might be a few redundant things that we can either outright eliminate or merge with other schemas. We're going to look at these 6 schemas here. Let's start with the case of weak entity sets. So section is a weak entity set whose existence depends on course. So the primary key of section is going to be the union of its discriminator and the primary key of course. So the primary key attributes are section ID, semester, year, and course ID. But look at section course. Those are the same attributes. Also, this identifying relationship set has no other attributes, no descriptive attributes. Therefore, the schema for section, it's the same thing as this section course relationship. Let's eliminate it. In general, if there is a weak entity set participating in an identifying relationship, a schema is needed for the strong entity set and the weak entity set. We do not need to add one for the identifying relationship set. So, schema for course, yes. Schema for section, yes. Schema for section course, not needed because it's going to be the same thing as section. How about the other schemas? Well, let's first consider entity sets A and B participating in relationship set R. Following all the rules as before, we then create schemas for A and B and R with the following attributes. Let's assume that A and B have 2 attributes each, and a third one each for their primary keys. That means the relationship set schema then has 2 primary key attributes. But what if A and B participate in a many-to-one relationship and A's participation is total? This means every entity in A will show up in the schema for A, and those same entities will all show up in the schema for R. See where this is going? If all the same entities are going to show up in A and R, then to simplify things, let's just combine A and R together. So, when we merge A and R this way, we only need one primary key, and that is the primary key of A. We don't need the primary key of B to be in here. So the primary key attributes of B, we do not need to have them, we don't need them to be primary key attributes of A. So B key attribute is just another attribute. So when we combine A and R, we just combine all their attributes together, and the primary key of A becomes the primary key of this new combined relation. Well, I should say schema. And now we can apply the same logic to instructor department. Since every instance of an instructor is going to show up in instructor department, we're just going to combine this schema with instructor. So this is how we end up with department name as an attribute for instructor. We started off with eliminating it, and now we just added it back. It's a little bit it's a little bit screwy, but this is just the nature of making an ER diagram. So we combine instructor and instructor department into one relation, instructor. We add department name as another attribute for instructor. The ID, that is the primary key, stays the primary key. The same thing is true for student department. We just take the department name attribute and just add it to student. More accurately, we combine. Okay, so I guess there's an error. This is supposed to be student. So we combine student and student department. Let me just fix that real quick. So, come on. So we merge instructor and instructor department together. We merge student and student department together. We merge course and course department together. And we can keep going, but let's see why we can merge these schemas. Let's look at the one for student and department. In the ER diagram, a student can be associated with one or more departments, so we express that as a relationship set between students and departments. However, we have total participation for student, and we also have a one-to-many relationship, one-to-many mapping between departments and students. So a department can be associated more than one. A student can be associated with more than one department, and we want every student to participate in this student-department relationship. Those are the exact conditions under which we can combine schemas. So we just combine student and student department as one schema. And this even works if we have partial participation. If we have that just means that a student has yet to choose a major. Now let's look at this foreign key constraints. Originally, the schema for R had two foreign key constraints since it was referencing A and B. When we combine A and R together, we drop the foreign key constraint with A, and we keep the one with B. So now A has a foreign key constraint with B. And what this means for our students is this. Students can only be associated with departments that exist in our university. So they can be associated with the math department, but not a department store or the Department of Defense. Even though those are departments, they're not departments at the university. They're the wrong kinds of departments. So out of our 10 schemas for our relationship sets, we did not need 6 of them. Of those 6, 1 was redundant and the other 5 were merged with other schemas. So now we can combine that with the schemas for our entities, and this is our final schema for our university. In the following chapters, we're going to turn these into tables in a database. So the last several slides in here is just design issues with ER diagrams. I'm just going to summarize the information shown here. Basically, there is an alternative way to represent phone numbers, and that is to argue that phone numbers are their own entity. So the question is, do you want to do this, or do you want to have phone numbers represent like this, or like this? There's no easy answer to that, because it depends on the semantics associated with the attributes in question. Likewise, it's not always clear to know when to express something as an entity set or a relationship set. Sure, we have this, but this is another way to represent things. Which one is better depends on what you're doing with that information. Also, turns out you can convert a non-binary relationship into a collection of binary relationship sets. This isn't always ideal, by the way. Where do you place attributes? Well, turns out there are other places we can place the date attribute, but those placements might not be ideal because they could be confused with, say, hiring date. Here's some extended features. Specialization and generalization. So, instructor and students are just specific instances of person. Instructor is a more specific employee. These are features that we don't talk about in our ER diagram, but they might be worth bringing up if you're familiar with, say, the idea of inheritance, specialization, and generalization. Also, some textbooks have different notation for ER diagrams. This is just the notation that's used in the book. So again, there's more than one way to represent the same thing. There's no one universal ER notation standard, nor is there one correct answer for every possible use case. Use your best judgment and follow the notation as closely as possible for whatever textbook you're following. With that said, let's turn one of these into a set of schemas. Okay. So I'm going to move this a little bit further up, and okay. Since all of these are pretty simple, let's just write the schemas for customer, car, and accident. So, customer, name, so for customer, that's pretty simple. It's the name, policy number, and other drivers, and we have the underlined policy number. For car, that's also pretty simple. Car, make, model, year, VIN, and that's underlined because that's the primary key, and accident. So let's write down accident, location, date, accident ID. There might be a few redundant attributes in here, but let's ignore that for now. And there we go. We have schemas for customer, car, and accident. So let's underline the primary key attributes, policy number, VIN, accident ID. There we go. Since many of these relationships are necessarily at least one-to-one or one-to-many, we can represent the schemas for drives as containing at the very least, we should have policy number, and VIN. But let's sit down and consider what attributes we really need. Since we have a one-to-many pairing between customers and cars, we could probably get away with only the VIN as our primary key here. Let's underline that. And since we have a one-to-many mapping between accidents and cars, let's write down involved in. Let's add the accident ID and VIN. But again, an accident can have... Hold on, let me think about this. Okay, so a customer can have one or more cars, so we can represent this drives relationship as having the primary key of VIN. For involved in, accident ID and VIN. This is a little bit tricky, so let's think about this. So an accident can involve one or more cars, but it turns out not every car can ever be involved. Not all cars need to be involved in an accident. So we're calling that these numbers apply. So an accident can involve one or more cars, but a car can be involved in 0 or more accidents. An accident involves one or more cars. A car can be involved in 0 or more accidents. So maybe we should swap this with this. An accident can involve one or more cars. A car can be involved in 0 or more accidents. There we go. So let's think about what kind of cardinality it's that, and let's pick out the appropriate primary keys attributes for that. So it turns out this is a car gets involved in 0 or more accidents, and an accident involves one or more cars. So we have a many-to-many relationship here, so we need both IDs. Is there anything else that we can eliminate? Well, a customer needs to have a car, because if they don't have a car, what's the point in them having car insurance? So we have a one-to-many mapping between customers and cars. So a customer can have one or more cars. So it turns out we might not need this drives relationship here at all. So that might be a little bit redundant to include. So what this means is now we have a one-to-many mapping between customers and cars. And remember this condition? If this is our customer and these are our cars, we have a one-to-many mapping, and every car is driven by a customer. We can combine the relationship. We can combine the schemas for drives with the one for customer. That means we don't need this drives relationship. We don't need that drives schema at all, and all you really got to do is add VIN as an attribute for customer. So that simplifies our schemas quite a bit. So now we have customer, car, accident, and involved in, which is a schema that requires two primary keys, two primary key attributes, accident ID and VIN. So now, I think we have a schema for our car insurance company. So here we go. That should be the full schema if we follow the rules correctly and use our best judgments to apply which rules apply here. So yeah, that's gonna be it for, hopefully that's gonna be it for our discussion on ER diagrams. And if you have any questions, definitely let me know, and I'll be uploading this as soon as possible so that you can view it and, well, follow along, okay? If you have any questions, we can just meet back up on Monday and talk about it then, okay? Alright,